Okay, this is going to be the last video where we're integrating via just doing the opposite of what we did with differentiation. After this, we're going to actually start getting into integration rules and how we can do stuff without knowing differentiation at all. But to start with, we're going to have a look at, well, it's called the reverse chain rule. Now, I don't like calling it the reverse chain rule because, in my opinion, it isn't one. It kind of is, but it isn't. So, if you remember the chain rule, and I'm going to use an example here. I'm going to say 2x plus 1 to the power of squared. 2x plus 1 squared. That's my y. If I wanted to differentiate this, do you remember what I did? I took the derivative of the interior, which is 2. I then took the power, multiplied it by it, minus 1 off the power, and wrote everything as it was. So that's the power of 1. And end up with 2x plus 1. And this is all fine, right? If you wanted to actually write it out with u substitution, etc., even better, go for it. But to do it quickly, this is what I get. So if I want to do this backwards to get integration, well, it gets a tad bit more annoying because there isn't really a method I can do to substitute and then work backwards and do things like that. So the way we do it is we use this reverse chain rule, but it's a bit more like trial and error. Let me show you what I mean. So, left me rubber. So, let's work backwards. So I know that dy dx of that, as I've just shown, is 4 times 2x plus 1 to the 1. So, this isn't a great example because of the 1, but we'll work with it. Let's say I was just given y equals 2x plus 1 to the 1. I'm not going to expand it out just because I want to pretend that number is something a bit more annoying than a 1. And I wanted to integrate this. The way that I would do that is I would look and I would recognize that this here looks oddly similar to what I would differentiate if I started with this. Now, you don't need to immediately recognize how all the numbers and everything works together. But what you do need to realise is that I'm basically starting with a 2x plus 1 squared. That bit should be obvious. Regardless of what's in front, this could be a mess in front, it could be a sine, a cos, a ln, or whatever in front. Regardless of what is in front, I should recognise that this 2x plus 1 squared is definitely going to have something to do with it if I want to work backwards. Because that 2 will always be brought down and we'll end up with 2x plus 1 to the 1. Now let's have a look at what's inside here. So inside here I've got 2x plus 1. So if I was going to differentiate that, I would pull out my 2. My 2 would go here, times by another 2, and I would get the 4. Which means, actually, pretty good, I've already got my answer. That's 2x plus 1, and here I get 2x plus 1, and then obviously when I minus 1 from that, I'll get 1. So I get my answer. But the official way to do it, because that number might not always be correct, this is just kind of a coincidence here, is to divide what I just pulled outside. So establish that once I get to this stage, I need to divide this thing here, so 2x plus 1, by that derivative on the inside, which is 2, and then divide it by the power, so divide it by another 2, and then add a power on top, so add a squared. So it's a bit confusing, and that gives me 2x plus 1, add the power back to the top, squared. It's a bit confusing, and this is why I don't like calling it the chain rule, or the reverse chain rule. When we have a reverse chain rule, to me that tells me there's a nice simple equation we put everything into, like the chain rule. But with this, it's a lot of trial and error and kind of guessing. So let me show you what I mean with another example. So, let's say we want to find the integral of cos of 4x dx. Well, similar to last time, I'm going to start off by thinking, what is this likely to look like? Well, when I integrate a cos, I end up with sine. Cos integrates to sine. So I know my final answer is going to have a sine in there somewhere. That's a good place to start. Now I need to think about what's going on with this 4x. Because if we think about it, let's say I start off with a sine of 4x, yeah? And then I differentiate this. Well, this is going to differentiate into, well, the 4 is going to be brought outside, the derivative here is going to be brought outside, so that'd be 4, and I'll end up with cos of 4x dx. And this is slightly more annoying because I've got a 4 here, and I don't have a 4 here. So the answer can't be sine of 4x, because then my initial starting point would have been 4 cos of 4x, but it's not. That 4 has disappeared. So how can I get rid of that 4? The answer is I can divide it before I even start. If I start off with a quarter of sine of 4x, when I differentiate this and I bring this 4 outside, that'll be 4 over 4 cos 4x, which is just cos of 4x plus c, which is my answer. This is where the trial and error comes in. We need to force it to work. If I just have the sine of 4x, it doesn't work because I don't have that 1 over 4. You will get the hang of this, I promise. I'll throw out a couple more examples just to be safe. So what about the integral of 2x plus 5 cubed dx? Okay, well, again, I'm immediately thinking, what is this going to look like if I were to work backwards, and what would I have to differentiate to get to this? Well, I'm immediately thinking it's going to have something to do with 2x plus 5 to the 4. Because whenever I differentiate anything to do with this, that 4 will be brought down, turn into a 3. So we've got the basic idea of what it's going to look like. Now we need to work on what comes before it. So there's nothing before this integral. So I need to work on getting nothing here. But let's differentiate this and see what happens. So I'm going to bring a 2 outside, which is the derivative of the interior. And I'm going to bring that 4 down. And then that 4 is going to turn into a 3. And I'm going to end up with 8 times 2x plus 5 cubed. But that is not what I started with. What I started with was nothing, well, 1 times 2x plus 5 cubed. There was no 8. Same as last time. How do I get rid of that 8? Well, I put it to be divided in the beginning. 1 over 8 times 2x plus 5 cubed, to the 4, plus c. Because if I differentiate this, the 4 gets brought down here, the 2 gets brought out here, and I get 4 times 2 divided by 8. 8 divided by 8 is 1. That becomes a cubed. That cancels to 1, and I'm left with what I started with. So it's very, very tricky to get the hang of this. Again, this is why I don't like calling it a rule. A rule should not involve this much trial and error, as far as I'm concerned. Last one, the integral of e to the 7x plus 2 dx. Once again, I know I'm probably going to end up with an e to the 7x plus 2 in my final answer, because if I were to work backwards, the derivative of e to the 7x plus 2 is going to have an e to the 7x plus 2 in it, because e doesn't change. But what do I need to have in front? Well, again, if I differentiate this, that is going to become 7 comes down, so it's 7e to the 7x plus 2. Well, that's not what I'm looking for up here. I need to have nothing in front of it, so I need to start off with a 1 over 7, e to the 7x plus 2 plus c. Because then if I differentiate this, my 7 comes down, cancels with that 7, and it disappears, as I need here. Reverse chain rule is not great. I don't like it. I think it's a bit wish-washy, but it does work. Just using our knowledge of differentiation and just keep checking what happens if I work backwards, what happens if I differentiate this, do I get my final answer? Then just playing around with the constants and the numbers involved, and eventually we'll get there. Starting next video, we'll start looking at actual rules of integration, not ones that are wishy-washy like this.